Okay, so I'm going to go over number 15 from the homework as sort of an introduction of today's lesson, but also just a reminder of what we did last lesson. And then we'll start today's lesson, which is 26.3. In 15, the question is, here's the function. And you have to find the inverse. I have the answer up here. Let's talk about how I got that. Of course, we flip x and y. Divide by 2. Square both sides. When I square this, I get x squared over 4. When I square this to the 1/2 and squared, makes it to the first power. Then I have to subtract the 5, which gives me this. Any questions on that part? Okay, so I'm going to put these kind of one on top of the other. If you only have this, that's a problem. That's a big problem. That was the hardest part of yesterday's lesson, but the most important part, because I know you guys knew how to do everything else except for to possibly add a restriction. You have to have this whole thing as your answer for inverse. Last hour, one person did. How many do we have this hour? Oh, how sad, guys. Good thing we're going over it. Now, let's just think of the parent function alone. Don't worry about the times 2 and the 5. If I do the parent function, which we all know is root x, we know that looks like this, right? Don't worry about anything else but the parent function. We know this parent function is x squared. Don't worry about the over 4 minus 5. Doesn't that look like this? Alarm bells are going off. There's no way that black graph can be reflected over the line y equals x. And suddenly now it looks like a U. Do you all see what I'm talking about? That's why I say a graph is not required, because it never says graph the function. It says find the inverse. And if you stop here, that's not the inverse. That's not how it works. So a graph is very helpful. So let me graph a little bit more in detail, but still a sketch. I'm going to graph this parent function. I have to move it over 5. Darn it. I've stretched it already. Over 5, and I purposely kind of made it stretch by a factor of 2, not necessarily to scale. Now I'm going to graph the parent function over here, x squared. You can also think of it like this. That's probably more helpful than x squared over 4, 1/4 x. So it's a parabola that has a vertical shrink and down 5. So something like this. That'd be a good sketch. Are those exact inverses reflection over the line y equals x? No. You are either going to pick this side of the vertex or this side. It does matter. My hope is that you can visualize it and know what side to pick. So we're visualizing it up here. Does it look like this is the side that I want to pick for reflection? Yes. If you're not sure, you can do some extra work to figure it out. I would say pick a point. Again, it doesn't have to be an exact point. For example, this point here. I don't know the number, but I know it's negative, right? Negative x direction. Is it in the positive or negative y direction? Positive. So when I flip x and y, my point here should be positive, negative. I need to go in the positive direction, then the negative direction. That makes that graph. So I go to the vertex, which in this case happens to be at an x value of 0, and I want numbers bigger than 0. Will it always be 0? No. It just depends where the function is located. If my function was here and I had to pick from the vertex here or here, I would have to say, oh, I'm at like -8 on the x, and I'm going to pick one side or the other. Questions? Okay, when you're doing inverses, some of you will get to a point where you just know which ones you have to restrict. We're not really there yet. So I would say graph them both and look at them. That looks like a good reflection, which is why it has to be the full answer. We are going to kind of skip around today. So I want to start us at, I'll take your scores at the end of the hour. Somebody remind me. Go to page 411, part A, please. 411, part A. You will find these are going to be easier, but I can kind of show you why. It says find the inverse. So let's do it together. You can work ahead if you want. Flip X and Y. I think there'll be enough room in your book. I know there's not a lot, but it's not many steps. Do both sides. So the inverse, x cubed minus 3. We should check to see if we need a restriction like we all forgot on that homework question. So you can watch or you can do this with me. I'm going to sketch the original graph. That parent function is cube root of x. It looks like this. This is your parent function. I need to move that 3 which direction? Left. Now this graph, that's your parent function x cubed. It's more of a vertical graph. Now it's going to move 3 which direction? Down. Do those look like a pretty good reflection over the line y equals x? Oh yeah, they do. Good news for you. They always will. When I give you an x cubed or a cube root, they are always going to be inverses without any restrictions. Here's the reasons there's no restrictions for these. The domain of this graph, the original, all real numbers. The range, all real numbers. There are no restrictions. So when I do the switch, there's still no restrictions on domain or range. The green is what you call 1-to-1. It passes the vertical and horizontal line test. So if I flip it, reflect it, it's still going to pass the vertical and horizontal line test. Questions on this one? Okay, do B, find the inverse. I'm going to do a sketch. Do a sketch if you have time. Finding the inverse takes about 10 seconds. To check on restrictions, we want to graph it, get a good visual, and see what we think. I've graphed my parent function, cube root, up 5. Now I'll graph this one down here, which is my x cubed function. And that's moved 5 to the right. Do those make a good reflection over the line y equals x? Yes. All the ones I give you, cube root and cubed, will. To remind you of what we did in the homework when it didn't, that was a square root, which looks like this, or some translation of that, left, right, stretch, shrink, up, down, and that inverse, which looks like this, which is a problem. Those have to be restricted. Now, if this was this graph, well, it would look like this, and then we would have no problems. But if it's just positive root x, then we're going to have a problem. All right. So all the ones I give you will be no restrictions. I do want to talk about some that I will give you that are goofy looking. I won't ask you to draw them. I will just ask you one small question. So let's take a look at number 4. Use a graphing calculator to investigate the graph of blank. Go ahead, read number 4, type that into your y equals in the normal 10 to 10 window. Cube root of x squared plus 4x. Hit graph. Does that look like something you've graphed before? No. Does that have a domain of all real numbers? Yes. Does it have a range of all real numbers? No. Every one we've done so far has. This one doesn't. Is this graph one-to-one passing the vertical and horizontal line test? No. What?
Why does she look like?
I'm going to show you. So I would not ask you to graph this without a calculator. What I would ask is something like, is this a function that's one-to-one? And you would be able to graph it and say yes or no. Here's what makes it different. This is not, yeah.
My calculator is not in English.
Second plus 712.
Okay.
Second plus 712, that'll reset everything. The reason this looks different and we get a different outcome is because this is not what we call a translation of the parent function. This doesn't mean I'm going to stretch by 2 and up 4 or right 4. That's why it's different. Everyone I've given you is a translation of the parent function. It looks like this. There could be a number here, plus or minus, a multiplication here, or a plus or minus here. But there is nothing else goofy happening. There are no x squareds. There's no 5x. That's what makes the difference. Let's look at number 5. Erase your current y equals and type in the function there that they have for number 5. Keegan, is yours good now?
No, it's still in the different language.
Okay.
I mean, I understand. It's like not like really different numbers.
Yeah, for the y equals button, it should still be the same. Your reset didn't help you?
No, it is no. Like if you hit like apps or whatever, like the words are not.
Here, you go to mode, and you go all the way.
Somebody was playing a silly little game.
Oh, she.
Yep, you're not the second one today, so I'm gonna pretty soon have to make calculators.
I kind of like this girl.
It's no longer an option for people who don't have them.
This one's not bad. The
I
other
know,
one's
some people
really
ruin it for others. Some people draw on them with my whiteboard markers. That makes me even more angry.
They draw on the calculators.
I just used this
Thankfully, it
one.
came off. Yeah, they were bored, so they just took their marker because we're doing whiteboards. They just took their marker and just drew vertical lines.
Why?
Black.
It doesn't even make sense.
I don't know. Don't know.
It doesn't even make sense.
And I can't figure out who did it because I don't have that many sets of eyes.
You should have like a sign out.
I know that will take extra class time and people will not write legibly and they'll like be, what calculator is it? Oh, I thought I had calculator too. It won't work. They're too immature to follow the current policy. So I'm not going to do extra work. I'll just not let them borrow them. Okay, so back to this one. Look at the function itself. If you've already hit the graph, that's fine. But does this look like a translation of the parent function?
No.
No, we don't look at this and say, okay, we're going to go vertical stretch by 6, reflect, up 5. That's not at all what this looks like. So I would give you this and I would say, graph it. Is it 1-to-1? And it most likely won't be. Which you can see in your graph, it passes the vertical line test, but not the horizontal. I could say without a calculator, write a function that has a cube or cube root that's not 1-to-1. So you might have to make one up. That won't be super difficult. Just do like x squared plus 7x plus 2 or just add extra squareds, whatever. Okay. Questions on that? Don't let those make you think it's all difficult. It's all good. If you can do A and B, you're good. Kind of a recap here on page 410. Go ahead and follow along as I read. Thus far, we have graphed and found the inverses of linear, exponential, logarithmic, quadratic, and square root functions. We discovered a number of patterns related to these functions. First, linear, exponential, log, square root functions always have inverses that are functions. Because up until yesterday, every function, we just found the inverse. We never even had to graph it to check anything because there never were any problems. So there's the list of all of the functions we've done before that we never even checked. Hey, should I restrict this? Do I need to graph it and check it? Nope. Till we get to that second bullet point, which is where the problems come in. Quadratic functions have inverses that are functions only if the domain is restricted. Otherwise, its inverse is a relation only. It doesn't mention, square roots are on the top. So I guess square root function was yesterday, and its inverse will be a function if we restrict it correctly. The third one, any function that is 1-to-1, remember it passes a vertical and horizontal line test, will have an inverse that is a function. If a function is not 1-to-1, the inverse will not be a function. It will be a relation only. It says, then let's explore some cube root and cubic functions to see if similar patterns exist. If we can determine whether a given cube or cube root function is 1-to-1, we will know if the inverse is a function. Study the graphs below. Each cubic graph at the bottom row is the inverse of the cube root graph above it in the top row. The graph in the center is the graphs in the center and right-hand columns are translations of the graphs of the parent functions, left-hand column. So we don't have to do anything. We're just going to kind of talk through this. You can see the top x cubed versus the parent function, and then we moved it up 4. Then we moved it over 3 and up 5. Then below that is the inverse. Let's talk about the domain. The domain of the first graph is negative infinity to infinity. Is that true for all 3 top graphs? Is that true for all 3 bottom graphs? Yes. The range for my first graph goes down forever and eventually goes up forever. Is that true of every graph in the top row? Every graph in the bottom row? Yes. Now here's my question. Will that be the domain and range? of every cube and cube root graph imaginable?
Yes.
Yeah.
Yes. We are going with the yes today.
Yes.
Now, didn't we just graph a cube function? It said x cubed, and it wasn't
Yeah, but that was nasty.
right.
But
So
whether they
it doesn't answer that question. The question was, is every cube or cube root graph imaginable going to have that property?
No.
No. If it is a transformation of the parent function, so if it's simply in this form, what do I want to do? Not, I want to do x. You can do plus or minus there. You can have a plus or minus here. That has to be an x. You can have any number there, positive or negative for stretch and shrink, and any number there. Any of those will be transformations, and yes, it will follow this. It will be 1-to-1. Its inverse will be a function of 1-to-1. Anything outside of this form, where there's like an x squared plus 3x, whatever, those are the crazy ones that you'll rarely see that will not follow these rules. But most of them will. Most of the ones you see will. Questions? Okie doke. You are ready for your homework.
Oh, that was bad.
Yeah, because they're a lot easier than yesterday's.
I kind of like the result.
Yeah, me too. I need to come around and get your homework.